If a stationary wall of high pressure sitting over the Midwest like a lid on a pressure cooker, and what it's doing to the soil, the crops, and the storm systems forming at its edges right now has you as locked in as it has me, hit like and subscribe to Signal Watch so you don't miss a single update as this story develops in real time. Drop a comment below and tell us where you're watching from, what time it is there, and this question. Have you noticed the ground cracking, the crops browning, or the sky doing something unusual in your region in the past 2 weeks? Because what you're about to see may explain exactly what you've been watching happen outside your window. And if you want to help this community keep growing, share this video on X, Facebook, Reddit, or even just your group chats. You're the reason we can keep chasing stories like this. So thank you for having our back. Now, a blocking ridge so stationary that the atmospheric models have been struggling to move it for 14 days straight, and what that tells us about the jet stream pattern that locked it in place. Soil moisture readings across a 6-state corridor that have dropped to levels not recorded since the summer of 2012. Lightning strikes igniting grassland with zero rainfall attached. Dry thunderstorms forming at the exact margins where this heat dome meets the atmospheric moisture it is actively blocking. And the compound fire weather scenario that fire behavior analysts are modeling in the corridors directly downwind. Now, settle in and let's get into it. There is a specific pattern in the upper level atmospheric flow that meteorologists track with a particular kind of attention. Not because it is rare, but because of what it does to every weather system that encounters it. It is called a blocking ridge, and when one locks into place over the central United States in the height of summer, the consequences for the land and the communities beneath it are not subtle, and they are not brief. The normal state of the mid-latitude atmosphere is one of continuous movement. The jet stream, the fast-moving ribbon of upper-level wind that encircles the hemisphere at altitudes between roughly 7 and 12 kilometers, typically progresses across the globe in a series of westward propagating waves carrying weather systems with it. Troughs of low pressure and ridges of high pressure embedded in the flow move generally from west to east, each one bringing its own character of weather, storms and cool air following the troughs, warmth and sunshine following the ridges, before giving way to the next pattern in the sequence. The average duration of a ridge over any given location in the continental United States in summer is 3 to 5 days. Uncomfortable heat, then relief. Blocking is what happens when this normal progression breaks down. A blocking ridge, also called an omega block, when the pattern takes the characteristic shape of the Greek letter in upper-level wind charts, with a high-pressure dome flanked by 2 troughs, is a ridge that resists the normal eastward progression. Instead of moving, it persists. Days pass, the ridge holds. Systems approaching from the west are deflected north or south around the block, like water parting around a boulder in a stream. The air beneath the ridge continues to sink, compress, and heat. The land beneath continues to lose moisture. The sun continues to bake the surface without interruption from cloud or rain. 14 days of a blocking ridge over a region is not a weather event. It is a transformation of the land surface. The specific blocking pattern that concerns the National Weather Service's Weather Prediction Center in College Park, Maryland, and the Climate Prediction Center in the same building is the one that combines 2 characteristics simultaneously: sufficient amplitude, enough northward displacement of the ridge axis to keep the jet stream well north of the affected region, blocking any storm systems that might provide relief, and sufficient persistence, a dynamical configuration that resists the normal mechanisms of ridge erosion, to extend the heat event well beyond the timescale that heat health advisories are designed for. The persistence of a blocking ridge is not random. It is connected to the broader configuration of the hemispheric jet stream pattern. Specifically, whether the flow is in a high amplitude, wavy state with large north-south excursions, or a low amplitude, more zonal state with the jet flowing roughly parallel to latitude circles. High amplitude wave patterns are more prone to blocking. They develop when temperature gradients between the tropics and the poles are disrupted in specific ways that the scientific literature has increasingly connected to Arctic amplification, the observed warming of the Arctic at rates approximately 4 times the global average that reduces the temperature contrast driving the jet stream's speed and stability. Jennifer Francis at the Woodwell Climate Research Center and her colleagues have published extensively on the proposed relationship between Arctic amplification and jet stream waviness, including the persistence of blocking events. The specific causal mechanism, whether reduced Arctic to mid-latitude temperature gradient produces more blocking or merely changes its character, remains an area of active scientific debate, with researchers including Elizabeth Barnes at Colorado State University offering alternative interpretations of the same observational data. What is not debated is the observation. Extreme, persistent heat events in the continental United States have been occurring more frequently and with greater intensity in the observed record of the past 2 decades than in the preceding half-century. The summer of 2012, when a blocking ridge locked over the central United States for an extended period and produced the most severe drought since the 1950s, with economic agricultural losses estimated at $30 billion, is the modern benchmark against which current conditions are measured. The summer of 2021's Pacific Northwest heat dome, which drove temperatures in Portland, Oregon to 46.6 degrees Celsius, more than 5 degrees above the previous all-time record, and killed approximately 800 people in British Columbia alone, is the benchmark for what blocking ridge extremes can produce at the upper tail of the intensity distribution. The current event is being compared to both. The term heat dome entered public meteorological vocabulary in the coverage of the Pacific Northwest 2021 event and has since become standard in media and NWS public communications. It is accurate as a physical description, and understanding the precise physics it encodes is essential to understanding why the current pattern is doing what it is doing to the land beneath it. A heat dome is a ridge of high pressure in the upper atmosphere, specifically in the 500 hectopascal pressure level that meteorologists use as the standard reference for mid-tropospheric flow, typically at an altitude of approximately 5.5 kilometers above sea level. High pressure at this level means the air column is warmer and more buoyant than surrounding columns, causing it to extend higher, like a warm bubble in a fluid. The 500 hectopascal surface is displaced upward in the ridge compared to surrounding areas. Within the ridge, the large-scale atmospheric motion is dominated by subsidence, sinking air. Air that descends from the upper troposphere compresses as it encounters higher atmospheric pressure at lower altitudes. Compression heats the air through adiabatic warming, the same process that heats air in a bicycle pump when you compress it quickly. The rate of adiabatic warming is approximately 10 degrees Celsius per kilometer of descent for dry air. An air parcel descending 5 kilometers through a ridge from its origin at upper levels warms by approximately 50 degrees Celsius in the absence of evaporative cooling. This subsiding, adiabatically warmed air suppresses cloud formation. Clouds form when air rises, cools, and reaches saturation. Subsiding air warms and dries. It does not saturate. It does not form clouds. The sky beneath a blocking ridge is relentlessly clear. Clear sky means uninterrupted solar insolation, the direct heating of the Earth's surface by sunlight. At summer solstice, latitudes in the central United States, the solar energy input to the surface on a clear day is approximately 900 to 1,000 watts per square meter at peak. That energy must go somewhere. In a normal summer pattern with some cloud cover and vegetation-driven evapotranspiration, returning moisture to the atmosphere and cooling the surface, the energy is partitioned between sensible heat, direct warming of the air, and latent heat, evaporation of water from soil and plant surfaces. When the soil dries out, the latent heat pathway closes. There is no more water to evaporate. All of the incoming solar energy goes into sensible heat. Surface temperatures spike. Near-surface air temperatures, driven by the superheated land surface, radiating long-wave energy upward into the boundary layer, rise toward and beyond 40 degrees Celsius across wide areas. The heat index, the apparent temperature that accounts for humidity's effect on the body's ability to cool itself through perspiration, can significantly exceed the air temperature when heat is combined with moderate humidity. In the specific scenario of a blocking ridge over the central United States, the low-level flow of humid air from the Gulf of Mexico continues to advect moisture northward into the southern and central portions of the blocked region, even as upper-level subsidence suppresses any deep convection that might relieve it. The result is air temperatures above 40 degrees Celsius, combined with dew points above 25 degrees, heat index values above 50 degrees Celsius or higher. At heat index values above 50 degrees Celsius, the human body cannot maintain a safe core temperature through perspiration alone, regardless of activity level. The wet bulb globe temperature, the composite measure of heat, humidity, radiation, and wind used by the military, athletic organizations, and occupational health authorities to assess outdoor heat exposure risk, enters the range where outdoor physical activity produces health risk, even in acclimatized adults within 30 to 60 minutes. For elderly populations, individuals with cardiovascular or respiratory conditions, outdoor workers, and people without access to air conditioning, the heat event beneath a blocking ridge is not discomfort. It is a medical emergency. The 175 deaths in the Pacific Northwest 2021 event were disproportionately concentrated in elderly individuals living alone, without air conditioning, in a region where the historical climate had never made air conditioning standard residential infrastructure. The lesson is not specific to the Pacific Northwest. The Midwest contains large rural and small town populations where air conditioning is inconsistently available, where elderly populations live independently, and where heat emergency services are sized for historical heat event frequencies rather than the blocking ridge scenario unfolding right now. The term drought in common usage implies a gradual process. The slow accumulation of precipitation deficits over months and seasons that progressively dries soil, depletes reservoirs, and stresses vegetation. That understanding, accurate for the slow onset drought events that characterize the historical agricultural record, is inadequate for what a blocking ridge produces in the age of anomalously warm background temperatures. A flash drought is a rapid onset, rapid intensification drought event driven not primarily by precipitation deficit, but by anomalously high evaporative demand, the rate at which the atmosphere pulls moisture from the soil and vegetation surface. The term was formalized in the scientific literature by Mark Svoboda at the National Drought Mitigation Center and colleagues, and has been developed extensively by Jordan Christian at the University of Oklahoma and Jason Otkin at the University of Wisconsin, whose work defined flash drought in operational terms as a period during which drought intensity increases by at least 2 categories on the U.S. Drought Monitor scale within 5 weeks. 2 categories on the U.S. Drought Monitor in 5 weeks. The Drought Monitor uses 5 intensity categories: D0, abnormally dry; D1, moderate drought; D2, severe drought; D3, extreme drought; D4, exceptional drought. A 2-category jump in 5 weeks means moving from D0 to D2, or from D1 to D3 within the span of a single weather pattern. The physical mechanism is direct. Potential evapotranspiration, the rate at which water would evaporate from the land surface if water were freely available, is driven by temperature, solar radiation, wind speed, and atmospheric humidity deficit. All 4 drivers are simultaneously elevated beneath a blocking ridge. Temperatures are extreme. Solar radiation is uninterrupted by cloud cover. Wind scours moisture from exposed soil surfaces, and the low humidity of the subsiding air creates a steep atmospheric moisture gradient that pulls water from soil pores. The evaporative demand beneath a blocking ridge can be 2 to 3 times the rate that the same region experiences on a typical summer day. When evaporative demand exceeds precipitation, which, beneath a blocking ridge that has suppressed all convection for 2 weeks, it does, by an enormous margin, soil moisture depletes. First, the upper soil layer dries, the top 10 to 30 centimeters that most row crops' root systems depend on. Then the intermediate layer at 30 to 60 centimeters. Then, in an extended event, the deeper rooting zone at 60 to 100 centimeters where more drought-tolerant crops, and established pasture grasses draw water. The USDA's Natural Resources Conservation Service operates the SNOWTEL and SCAN networks, the snowpack telemetry and soil climate analysis network systems that provide near real-time soil moisture data at hundreds of stations across the United States. The SCAN station data for the affected Midwest corridor, downloaded from the NRCS National Water and Climate Center portal, is showing soil moisture values in the upper soil layers that have dropped to soil type specific field capacity percentages consistent with severe drought in some areas, values that the stations in the same network recorded during the 2012 drought and in only 2 to 3 other summers in the full period of record. The agricultural consequences are not deferred to the end of the growing season. They are happening on the timescale of the event itself. Corn, the primary cash crop of the affected corridor, reaches its critical moisture demand period during pollination, the period roughly 60 to 75 days after planting, when the pollen shed and silk reception that determines kernel set occurs over a window of approximately 1 week. Soil moisture stress during pollination directly reduces yield. Temperatures above 35 degrees Celsius during afternoon peak heat cause pollen sterility. The pollen desiccates before it can fertilize the silk. Heat stress and soil moisture stress together, simultaneous during the pollination window of a corn crop that was planted on schedule in May and is now in its critical period, can reduce yield by 50 to 90% in a single week of exposure. The USDA's National Agricultural Statistics Service Crop Progress Report, released each Monday during the growing season, will show the consequence of the current event in its crop condition ratings for the affected states. The ratings, measured on a scale from very poor through poor, fair, good, and excellent, are the operational signal that agricultural commodity markets, crop insurance adjusters, and food security analysts are watching. A shift of 20 to 30 percentage points from good to excellent into poor to very poor in a single week's report is not an abstract statistic. It is the economic destruction of a year's agricultural production for tens of thousands of farming operations. The soil moisture data deserves its own examination because it is the physical link between the atmospheric blocking pattern above and the fire weather catastrophe that is building at the margins of the heat dome below. It is not a derived or modeled quantity. It is a direct measurement from sensors in the ground, and the sensors across the affected corridor are telling a specific story. Soil moisture is measured by the SCAN network sensors using 2 primary methods: time domain reflectometry, which measures the dielectric permittivity of the soil, a property that changes dramatically depending on how much water is present, and heat dissipation sensors that infer moisture from the rate at which heat conducts through the soil matrix. The measurements are expressed as volumetric water content, the fraction of the soil volume that is occupied by water, in cubic centimeters per cubic centimeter. Field capacity, the moisture content at which the soil holds as much water as it can against gravity, with the excess having already drained, is the upper reference point, the permanent wilting point, the moisture content below which plant roots cannot extract water from the soil, regardless of how much appears to be present, because it is held too tightly by capillary forces in the soil pore structure, is the lower reference point. Between field capacity and wilting point is the plant available water. Below the wilting point, the water is there in a physical sense, but is inaccessible to plant roots. The crop dies. The SCAN stations in the affected corridor are recording values in the upper soil layers that are approaching, or in some cases crossing below, the permanent wilting point for the loamy and silty clay loam, soils characteristic of the Corn Belt. This is not marginal stress. Plants experiencing soil moisture below the wilting point are not simply stressed. They cannot take up water. Their stomata close in a final attempt to conserve what little moisture remains in their tissues. Photosynthesis shuts down. Cellular damage begins. The crop is functionally dead days before it appears visually dead, the greening delay that lulls observers into underestimating the severity of the damage before the visible wilting and browning that follows. The spatial extent of the soil moisture collapse is mapped in near real time by the North American Land Data Assimilation System, NLDAS, which ingests precipitation, temperature, radiation, and other forcing data to drive land surface models that estimate soil moisture across the continent on hourly timescales. The NLDAS soil moisture anomaly maps, showing departure from the 1979 to 2010 climatological mean for the corresponding date, are available through the National Centers for Environmental Prediction and show a coherent region of severe negative anomaly centered on the blocked region that is expanding in spatial extent with each passing day of the heat event. The expansion matters because soil moisture anomalies affect the boundary layer atmosphere. Dry soil has a lower thermal capacity than moist soil and reflects less solar radiation, a lower albedo. The combination of lower heat capacity and lower albedo means dry soil heats more rapidly and to higher temperatures than moist soil under the same solar input. Hotter surface temperatures drive deeper, more intense convective mixing in the boundary layer. A deeper, more intensely mixed boundary layer is a drier boundary layer. Moisture is diluted through a greater depth of air. A drier boundary layer has lower relative humidity at all levels, which increases the fire weather danger in two simultaneous ways. It desiccates surface fuels more rapidly, and it provides a less humid atmosphere into which lightning-ignited fires can spread. The soil moisture collapse is not just an agricultural catastrophe. It is the preparation of the landscape for what comes when the dry thunderstorms begin. A blocking ridge does not simply sit over a region passively while the land bakes beneath it. At its margins, the zones where the subsiding, moisture-suppressing high pressure encounters the atmospheric flow that it is deflecting around its boundaries, a specific and dangerous meteorological interaction is occurring. The mid-level flow around the flanks of a blocking ridge carries moisture-laden air from the Gulf of Mexico and the adjacent regions of the atmosphere into the margins of the high. As this moisture encounters the warm, unstable boundary layer air that is pooling at the edges of the blocked region, air that has been heated by weeks of intense surface warming, but that has not had the deep convective pathway through the high pressure suppression to release the instability it has accumulated, the thermodynamic ingredients for thunderstorm development are present. Instability, lift from the mid-level flow disturbances skirting the ridge, moisture in the mid-levels. What is not always present is low-level moisture. At the surface, beneath the heat dome and extending to its margins, the weeks of evapotranspiration of soil moisture have depleted the boundary layer humidity. The lifted condensation level, the altitude at which rising air cools to its dew point and condensation begins, is extremely high because the low-level dew points are low in the desiccated boundary layer. Thunderstorms that develop in this environment have a peculiar and dangerous vertical structure. Cloud bases at altitudes of 3,000 to 4,000 meters or above, instead of the typical 1,000 to 1,500 meters of a storm, developing in a humid boundary layer with the precipitation generating upper portions of the storm extending to 12,000 meters or more. The precipitation that forms in the upper levels of these storms, the water droplets and ice crystals produced in the cold, moist air above the high cloud base, falls toward the surface, but it falls through kilometers of extraordinarily dry, hot air below the cloud base. In a normal, humid season thunderstorm, precipitation reaches the surface as rain. In the dry, hot air beneath these elevated cloud bases, the falling precipitation evaporates before reaching the ground. The meteorological term for this phenomenon is virga, the visible streaks of precipitation descending from storm bases that dissipate before hitting the surface. The storms produce lightning. They do not produce rain at the surface. The lightning is dry. The Haynes Index, an operational fire weather index developed by Albert Haynes at the USDA Forest Service in 1988 and used by the National Weather Service's Fire Weather Forecast Program, measures the combination of atmospheric instability and dryness in the lower atmosphere that promotes the development and spread of wildfire. The index ranges from 2 to 6, with values of 5 or 6 indicating high potential for large fire development. The Haynes Index across the heat dome margin region is currently running at 5 to 6 across much of the affected area, the maximum fire weather danger classification. The red flag warning, the NWS product issued when a combination of critical fire weather conditions, including low relative humidity, high winds, and dry fuels, produces a risk of rapid fire spread, is the operational threshold that triggers coordinated responses from state forestry agencies, the USDA Forest Service, the Bureau of Land Management, and local fire departments. Red flag warnings across the states at the margins of the current heat dome are not single county or isolated events. They are covering multi-state areas simultaneously, driven by the same atmospheric configuration that is producing the dry thunderstorm threat. Here is where the investigation earns its technical depth. Because understanding the current blocking ridge and what it is doing to the operational forecast models requires going inside the dynamics, through the specific products and model outputs that the Weather Prediction Center meteorologists are working with, and the specific ways those products are telling a story that the public forecast communications are still catching up to. The primary operational medium-range forecast models used by the NWS are the Global Forecast System, GFS, run 4 times daily by NOAA's Environmental Modeling Center, and the European Center for Medium-Range Weather Forecasts, ECMWF model, widely considered the most skillful global forecast model in operational use. The ECMWF model's superior skill relative to the GFS at forecast ranges beyond 3 to 5 days, has been documented in repeated verification studies, and is the reason that NWS meteorologists routinely compare GFS and ECMWF model output as part of their forecast workflow. For blocking events, both models struggle. Blocking is one of the most persistent biases in numerical weather prediction. Models consistently underestimate the persistence and intensity of blocking ridges because the underlying mechanisms that sustain a block involve planetary wave dynamics and teleconnections between distant parts of the atmosphere that require enormous spatial scale to represent correctly and that interact with parameterized processes, friction, convection, radiation, in ways that accumulate errors over the medium range. The ECMWF ensemble, the ensemble prediction system that runs 51 members of the model with slightly different initial conditions to characterize forecast uncertainty, is the most reliable tool for assessing how confident meteorologists should be in specific outcomes at ranges of 7 to 14 days. When the ECMWF ensemble shows a large spread in the position and intensity of the blocking ridge at the 10 to 14 day range, when the 51 members disagree substantially about whether the block erodes, intensifies, or shifts, meteorologists interpret that spread as genuine uncertainty about the event's evolution. When the ensemble shows a tight clustering of members, all maintaining the block in roughly the same position, when the spread is small, that clustering means the atmospheric dynamics are confidently favoring block maintenance. The current ECMWF ensemble guidance, available to operational meteorologists through the NOAA NWS's model analysis tools, has been showing the latter: persistent, confident maintenance of the blocking ridge with low ensemble spread at forecast ranges that would normally produce substantial spread for a 2-week event. Low spread with a persistent block. That is the pattern that produces the Weather Prediction Center heat advisories, extending further into the future than the typical 5-day outlook period. That is the signal that climate prediction offices translate into agricultural drought monitor updates. And it is the signal that fire weather forecasters are using to project the duration and spatial extent of the red flag warning conditions at the heat dome margins, the 500 hectopascal height anomaly maps, the standard diagnostic for blocking ridge strength, showing how much higher the mid-troposphere is over the blocked region compared to climatological norms, are showing positive anomalies of over 200 meters over the core of the blocked region. 200 meters of positive height anomaly at 500 hectopascals is a substantial blocking event. The 2012 Mid-Continent Drought Block produced comparable anomalies at its peak. The 2021 Pacific Northwest event produced anomaly values approaching 300 meters at its most extreme. Values that were, in the words of NWS Portland meteorologist Scott Sistek in his post-event analysis, essentially off the historical charts. The current events anomaly values place it within the upper tier of documented blocking events in the continental United States historical record. Whether it matches or exceeds the historical extremes depends on how long it persists, and the ensemble is currently not showing resolution. And this is where the story takes the turn that transforms a heat event into a fire catastrophe. The specific atmospheric mechanism by which the heat dome creates the exact conditions for lightning-ignited fires in landscapes that have been prepared for ignition by weeks of desiccation. The dry thunderstorm is not a rare or exotic phenomenon. It is a recurring feature of the western and central United States fire weather landscape, documented in National Interagency Fire Center incident reports, in NOAA storm data publication records, and in the Fire Weather Forecast Program's operational guidance dating back decades. The Phoenix Lightning Fire Complex of July 2021 in Northern California, the August 2020 Carmel Fire near Big Sur that began from dry lightning, and the August 2020 Lightning Complex fires across Northern California that ignited more than 1,000 individual fires over a 72-hour period, burning approximately 1.2 million acres and overwhelming fire suppression resources across the state, are all products of this mechanism. The physical sequence is well understood. A mid-level disturbance, a short-wave trough, or a mesoscale convective vortex rotating around the margin of the blocking ridge provides upper-level lift over the desiccated, unstable air mass at the heat dome edge. Convective development begins. The storms that form have the elevated cloud bases characteristic of high-based convection in a dry boundary layer, bases at 3,000 to 4,000 meters, sometimes higher. The equilibrium level of the storms, the altitude at which the buoyancy of the rising air is neutralized and vertical development stops, is at the tropopause, typically at 12 to 14 kilometers. The column of atmosphere within these storms is therefore approximately 10 kilometers tall, from cloud base to cloud top. The upper levels of the storm are cold, moist, and electrified. The charge separation that produces lightning occurs through the collisions between ice particles and supercooled water droplets in the mixed phase zone of the storm, typically at altitudes of 5 to 8 kilometers, where temperatures are between roughly -10 and -25 degrees Celsius. This process is the same in dry thunderstorms and in rain-producing thunderstorms. The charge separation mechanism does not know or care whether the precipitation that falls from the storm will reach the surface. The precipitation reaches cloud base as rain or hail and begins its descent through the subcloud layer. In a humid season storm where the subcloud layer is moist, the rain falls through air that is near saturation. There is little evaporative capacity, and the precipitation survives to the surface. In the dry thunderstorm environment, the subcloud layer is extraordinarily dry. The surface dew points beneath the heat dome margins may be in the single digits to low teens Celsius. The wet bulb temperature at cloud base level is far below the actual air temperature. The evaporative capacity of the subcloud air is enormous. Raindrops of typical size, 1 to 3 millimeters diameter, have fall distances of 3 to 4 kilometers to travel before reaching the surface, all of it through air that is aggressively evaporating them. The precipitation evaporates. The latent heat absorbed by that evaporation cools the subcloud air and accelerates its descent. The same downdraft dynamics that produce outflow in a normal storm, but now strengthened by the large evaporative cooling signal from the complete evaporation of the precipitation shaft. The downdraft reaches the surface as a gust front, a pulse of cold, dry, fast-moving air spreading outward from the storm base. That gust front dries and fans any fire that has been started by the lightning. The lightning, meanwhile, strikes the surface. The stroke heats the air in the lightning channel to approximately 30,000 degrees Celsius, roughly 5 times the surface temperature of the sun, for a fraction of a second. The superheated channel ignites any dry fuel it contacts. In a landscape where soil moisture has been depleted below the permanent wilting point, where live fuel moisture contents in grasses and crop residue are below 10%, the level at which combustion is supported. and where dead fuel moisture contents in fine surface fuels may be below 5%, the ignition threshold is crossed by a lightning strike whose energy far exceeds what is required to initiate combustion. The gust front follows the ignition. The fire that a lightning strike has started in 100-hour fuels cured to single-digit moisture contents, hit by a 20 to 30 knot gust front of hot, dry air minutes after ignition, is not a fire that fire suppression resources arriving in 15 to 20 minutes will find small and manageable. It is a fire that, in the first 15 minutes, may already be running ahead of the gust front at speeds that preclude containment by any available suppression resource. The fire behavior of any wildland fire depends on the interaction between fuel, weather, and topography. The fire behavior triangle that the National Wildfire Coordinating Group's S290 Intermediate Wildland Fire Behavior course teaches as the foundational framework for fire analysis. In the current scenario, 2 of the 3 legs of that triangle have been systematically pushed toward the extreme end of their ranges by the heat dome event we have been examining. Fuel, the combustible material that provides the energy a fire consumes, is characterized in operational fire weather and fire behavior analysis by its moisture content, its continuity across the landscape, and its loading, the mass of fuel per unit area. Fine fuels, grasses, crop residue, small twigs, and leaf litter with diameters below 6 millimeters are called 1-hour fuels because their moisture content equilibrates with the atmospheric moisture within approximately 1 hour of exposure. They are the fuels that ignite most readily and carry fire most rapidly across the landscape. The 1-hour fuel moisture content across the heat dome region, calculated from the relative humidity and temperature data at remote automated weather stations. RAWS, operated by the Bureau of Land Management and the National Weather Service, is currently running at values of 3 to 7% across a wide area. 3 to 7%. The threshold at which the National Fire Danger Rating System rates fire danger as extreme. The highest category on the 7-category rating scale is approximately 7 to 9% for most fuel models in the affected region. The measured values are at or below this threshold across a multi-state area. The agricultural landscape of the Midwest, in a year when the corn and soybean crops have been killed or severely stressed by the flash drought, presents a specific fuel configuration that differs from the natural grassland or forest fires of the western United States, but carries comparable danger under the current conditions. Cured or dead corn stalks, desiccated to single-digit moisture content by weeks of extreme heat and soil moisture depletion, represent a discontinuous but extensive fine and medium fuel load. Soybean residue in fields where the crop has died before canopy closure represents a similarly desiccated light fuel layer. Grass and forb, fuels along field borders, roadsides, and in the grass waterways that characterize Midwestern agricultural landscapes are cured and available. The spatial configuration of agricultural fuels differs from rangeland or forest in one important way. It is interrupted by roads, plowed field buffers, and harvested areas that can impede fire spread. But it is connected in another important way. Drainage corridors, grass waterways, roadside vegetation, and unharvested field margins form semi-continuous pathways along which fire can propagate rapidly under high wind conditions, connecting isolated ignition sources into running fires that move through the agricultural landscape faster than rural fire departments operating on multi-mile response time frameworks can intercept. The topographic leg of the fire behavior triangle is in the flat to gently rolling terrain of the Corn Belt, generally less influential than in the western United States, where canyon topography and slope aspect create extreme fire behavior through chimney effects and slope-driven uphill runs. The relatively benign topography of the Midwest is one of the factors that has historically kept fire danger assessments for this region lower than for the western states. Under the specific combination of cured agricultural fuels, single-digit moisture content, and the gust front dynamics of dry thunderstorm outflow, flat topography provides an efficient pathway for rapid fire spread in all wind directions without the channeling constraints of terrain. The National Interagency Fire Center in Boise, Idaho, is the coordination point for wildfire resource management across the federal government. the place where Type 1 incident management teams are pre-positioned, where air tanker base assignments are made, where the 10-day wildfire outlook products are produced. The National Fire Danger Rating System's forward outlook for the current fire weather pattern is being produced daily by the Predictive Services Offices of the Geographic Area Coordination Centers, the regional coordination units that manage fire resources across geographic areas. The Predictive Services Fire Weather Outlook for the area affected by the current heat dome is, in the language of these products, describing conditions consistent with the potential for large fire development. Large fire development, the operational term for fires that exceed the initial attack suppression capability of the first responding resources and require extended attack with additional resources, is not a universal consequence of every red flag warning period, but the specific combination of factors present in the current scenario has been associated with large fire development in the documented historical record. The HISPLIT trajectory model, the NOAA Air Resources Laboratory's atmospheric transport and dispersion model, used in smoke forecasting, is being run by the National Weather Service's Fire Weather Program to project the transport of smoke from potential fire starts in the red flag warning area. The model outputs show smoke transport corridors extending hundreds of kilometers downwind from the most probable ignition zones. Transport pathways that pass over suburban and urban areas downwind of the agricultural and grassland fire corridors. Smoke transport at concentrations sufficient to exceed EPA air quality standards. The 24 hours average PM 2.5 standard of 35 micrograms per cubic meter under the National Ambient Air Quality Standards can affect populations far from the fire perimeter. The 2020 California Lightning Complex fires produced smoke that elevated PM 2.5 concentrations to hazardous levels above 250 micrograms per cubic meter across the San Francisco Bay Area and Sacramento Valley for multiple days, affecting approximately 8 million people. The health consequences of acute wildfire, smoke exposure at those concentrations, respiratory distress, cardiovascular stress, exacerbation of asthma and COPD fall disproportionately on the same vulnerable populations that are already at elevated risk from the heat dome event itself. A large fire event in the current scenario would not be an isolated Western states phenomenon. It would be a Midwest event occurring in a region whose fire suppression infrastructure, the number of Type 1 incident management teams, the air tanker base capacity, the bulldozer and hand crew resources is sized for the historical fire frequency of the Corn Belt, not for a Western states scale fire weather episode in a landscape prepared by a flash drought. This investigation has been building toward the recognition that the heat dome is not a single hazard event. It is a compound event generator, a persistent atmospheric pattern that simultaneously creates multiple distinct hazard pathways that interact with each other and with the human and agricultural systems in the affected region in ways that amplify the total consequence beyond what any individual hazard pathway produces alone. The compound event framework that this channel returns to across investigations is precisely applicable here. Heat dome creates direct human health hazard, heat-related illness, and death for vulnerable populations. Simultaneously, heat dome creates flash drought through enhanced evaporative demand, direct agricultural economic loss, and food supply disruption. Simultaneously, flash drought desiccates fuels and prepares the landscape for ignition, fire weather hazard. Simultaneously, the heat dome margins generate dry thunderstorms, ignition sources arriving at the exact moment the fuel preparation is most extreme. Simultaneously, the dry thunderstorm, gust fronts, and outflow boundaries create extreme fire spread conditions, converting ignition into large fire development. And the smoke from large fire development creates an additional air quality hazard that falls on populations already stressed by the heat event. These pathways are not additive, they are multiplicative. A human health system managing heat emergency calls simultaneously with fire evacuation coordination, simultaneously with agricultural disaster assessment, simultaneously with air quality health advisories is a system operating at multiples of its historical baseline load, with each hazard pathway competing for the same response resources: emergency management personnel, public communications capacity, healthcare system bandwidth. The emergency management research on compound events, specifically the work of Zach Zobel and Michael Weiner at Lawrence Berkeley National Laboratory on co-occurring climate extremes, has established that the probability of multiple extreme events occurring simultaneously in the same region has increased substantially in the observed climate record of the past 3 decades. Their analysis, published in Nature Climate Change, showed that the joint probability of heat and drought co-occurring in the central United States has increased by a statistically significant margin above what would be expected from the individual trend in each variable alone. The correlation between the two hazards has increased, which means that large heat events increasingly co-occur with large drought events in ways that the historical independence assumptions of risk models underestimate. The fire weather connection adds a third correlated hazard to the pair. Heat and drought and fire weather are not 3 independent draws from independent probability distributions. They are driven by the same atmospheric forcing, the blocking ridge, and therefore co-occur at rates that far exceed the product of their individual probabilities. Every risk model calibrated on historical hazard independence is underestimating the probability of the compound scenario that is currently unfolding. The agricultural damage from a flash drought is not a future projection. It is being recorded in real time by the instruments and assessments that track crop condition across the affected region, and the numbers are telling a specific story about the scale of economic loss that is accumulating with each day that the blocking ridge holds. The USDA's National Agricultural Statistics Service publishes crop progress and condition reports each Monday during the growing season, tracking the percentage of corn, soybeans, winter wheat, and other major crops rated in each condition category across all major producing states. The reports draw on field surveys by USDA field statisticians in each state, supplemented by satellite-derived vegetation indices, specifically the Normalized Difference Vegetation Index, or NDVI, from the MODIS instrument aboard NASA's Terra and Aqua satellites, which measures plant greenness and by proxy plant health and moisture stress. The NDVI anomaly maps for the affected region, showing departure from the 5-year mean for the corresponding date, are showing negative anomalies across broad swaths of the primary corn and soybean production areas of the affected states. Negative NDVI anomalies indicate that the crop canopy is less green, less dense, or less healthy than typical for this point in the growing season. The spatial pattern of the anomaly corresponds closely to the spatial pattern of the soil moisture deficit as measured by the NLDS system and the SCAN network, the same areas that have been most intensely affected by the blocking ridge's evaporative demand are showing the most severe vegetation stress. The economic arithmetic of crop loss in the primary corn and soybean production states is not abstract. The affected corridor, roughly from the western portions of the Corn Belt through the Great Plains Transition Zone, typically produces a substantial fraction of the national corn and soybean crop. USDA's World Agricultural Supply and Demand Estimates report, published monthly, provides the benchmark for production forecasts. A reduction of 20 to 30% in corn yield across the affected area, a conservative estimate for a flash drought event of the current intensity occurring during the pollination window, would represent a production decline of hundreds of millions of bushels relative to the preseason forecast. Agricultural commodity futures markets are already reflecting this assessment. Corn and soybean futures on the Chicago Board of Trade, where contracts for December corn delivery and November soybean delivery are the most active instruments during the growing season, have moved substantially in response to the unfolding drought signal. Commodity market responses are not merely financial abstractions. They drive the prices that grain elevator operators, livestock producers dependent on feed grain, and food processors pay for inputs. Price increases that ultimately reach consumers in the form of higher food prices at a lag of months. The livestock sector adds a second layer to the agricultural damage. Cattle ranchers and dairy operators in the affected region depend on pasture and forage grasses that are experiencing the same desiccation as the row crops. Hay production, the primary winter feed reserve for cattle operations in the region, is being dramatically reduced in the affected areas. when the flash drought kills or severely stresses the first hay cutting of the season. The second cutting, which normally provides a reserve for winter feeding, is also affected if the drought persists into late summer. Ranchers making decisions about whether to sell cattle now versus hold through what may be a feed-scarce winter are making irreversible economic decisions under genuine uncertainty about how long the event will persist. The human health consequences of the current heat dome event are distributed unequally across the affected population in patterns that reflect the intersection of physiological vulnerability with socioeconomic access to protective resources. That intersection produces a risk map that is not simply the air temperature map, it is the air temperature map filtered through the distribution of air conditioning access, outdoor occupational exposure, chronic health conditions, and social isolation. The National Weather Service's heat alert hierarchy, heat advisory, excessive heat watch, excessive heat warning is calibrated on the heat index, the apparent temperature that accounts for humidity's effect on the body's cooling capacity. An excessive heat warning, the highest tier, triggered when heat index values meet or exceed threshold temperatures set by each local forecast office, based on regional climatology, indicates conditions that are dangerous for all people, not just vulnerable populations, when outdoor exposure is prolonged. The thresholds vary by region because heat risk is partly acclimation dependent. Populations accustomed to 95-degree summers have physiological and behavioral adaptations that populations in cooler climates lack. The Midwest forecast offices typically set excessive heat warning thresholds at heat index values of 40 to 42 degrees Celsius for 2 or more days, lower than the thresholds used by offices in the desert Southwest, where such conditions are more frequent and the population more acclimatized. The Cooling Center Network, the system of air-conditioned public facilities designated as official heat relief locations during heat emergencies, typically including libraries, community centers, and recreation centers, is the primary public health infrastructure for serving populations without home air conditioning. The network's capacity was sized based on historical heat event frequencies and historical air conditioning ownership rates. Air conditioning ownership in rural Midwest communities runs approximately 90 to 95% for primary residences, but in mobile homes, older rental housing stock, and for elderly residents on fixed incomes in small towns, access to air conditioning that is functional and affordable to operate is meaningfully lower. The medical research on heat mortality is clear about who dies in major heat events. The European heat wave of August 23, 2003 killed approximately 70,000 people across the continent, the deadliest heat event in European recorded history. The demographic profile of the victims was dominated by people over 75 living alone, people with chronic cardiovascular or respiratory disease, and people in urban environments where the urban heat island effect elevates temperatures above surrounding rural areas by 3 to 5 degrees Celsius at night. Night is critical. The human body repairs heat stress during the cooler overnight hours, and when nighttime temperatures remain above 25 to 28 degrees Celsius, the so-called warm night threshold, that repair window is eliminated and cumulative heat stress builds day over day. A blocking ridge event lasting 2 or more weeks produces multiple consecutive nights above the warm night threshold across the affected region. The health burden is not the product of a single extreme day. It is the cumulative product of 14 or more consecutive days without sufficient overnight cooling. By the second week of a blocking event, the most heat-vulnerable people in the affected region, the elderly living alone, the outdoor agricultural workers, the people whose window air conditioning units have failed or who cannot afford to run them continuously, are in a physiological state of significant cumulative heat stress, whose resolution requires either relief from the heat or access to medical intervention. The rural character of much of the heat dome affected region creates response infrastructure challenges that amplify the physiological risk. Rural emergency medical services typically operate with longer response times, smaller crews, and less specialized heat-related illness treatment capacity than urban EMS systems. The cooling center network in rural counties may consist of a single building in the county seat accessible only by vehicle. Elderly residents living on farms or in unincorporated communities may not have a neighbor who checks on them daily. The social isolation that characterizes rural elderly populations is itself a mortality risk factor in heat events, independent of the physiological vulnerability. The fire weather forecast cycle, the red flag warning issuances, the spot forecasts for individual fire incidents, the extended outlooks from predictive services is the operational interface between the atmospheric science this investigation has been building and the fire suppression and evacuation response systems that must act on it. The NWS fire weather forecasts are issued by local forecast offices using standardized products that specify the meteorological conditions relevant to fire behavior, relative humidity, wind speed and direction, temperature, and transport winds. The average wind in the column from the surface to the mixing height, which determines how rapidly smoke is removed from a fire area and how far it travels. The red flag warning polygon, the geographic area for which a red flag warning has been issued, is defined by the forecast office to cover the area where the combination of low humidity, high winds, and dry fuels simultaneously meets the threshold criteria. The current fire weather pattern shows a specific temporal evolution over the coming 72-hour period that fire weather forecasters are tracking closely. In the first 24 hours, the primary threat is from the dry thunderstorm complex that is developing along the northeastern margin of the heat dome, where mid-level moisture from a shortwave trough rotating around the blocking ridge is providing lift over the desiccated boundary layer. Isolated to scattered dry thunderstorms are expected, producing cloud-to-ground lightning with minimal or zero precipitation at the surface. The primary fire weather concern is lightning ignition in the red flag warning area, with subsequent fire spread under the outflow generated winds. In the 24 to 48 hour window, the shortwave disturbance passes and the primary threat transitions to the diurnally driven afternoon wind event, the afternoon heating cycle that drives mixing of stronger winds from the upper boundary layer to the surface, typically producing the period of maximum wind speed and minimum relative humidity between 2 and 6 p.m. local time. Fire starts from the previous night's lightning, which may have been smoldering in heavy fuels through the overnight hours, can transition to running fires when the afternoon winds arrive. In the 48 to 72 hour window, a second shortwave disturbance is being suggested by both the GFS and ECMWF model solutions, a second pulse of mid-level energy rotating around the persistent blocking ridge that could produce a second round of dry thunderstorms over an area that, if the first round has produced large fire growth, will already have activated fire weather response resources across the region. The compounding of a second ignition event on top of ongoing large fire management, the situation where fire suppression resources are already committed to managing first-round fire starts, and a second round of lightning is starting new fires, is the operational scenario that Geographic Area Coordination Centers are specifically preparing for in their resource pre-positioning decisions this morning. The investigation has been building a case about the specific meteorological event unfolding right now, but it cannot conclude honestly without addressing the question that situates this event in its larger context. To what degree is the current heat dome's intensity and the agricultural and fire weather consequences it is producing a product of the background warming of the climate system? The science of event attribution, the statistical and physical analysis of how much climate change has altered the probability and intensity of specific extreme weather events, has matured substantially in the past decade. The World Weather Attribution Consortium, co-led by Friederike Otto at the Grantham Institute at Imperial College London, and Geert Jan van Oldenborg at the Royal Netherlands Meteorological Institute before his death in 2021, has developed a rapid attribution methodology that can produce peer-reviewed attribution findings within days of major extreme weather events. The attribution methodology uses two types of analysis. The observational trend analysis examines the historical record of temperatures or related variables to detect and quantify any trend that has occurred over the period of anthropogenic climate forcing. The climate model analysis runs large ensembles of climate model simulations with and without the observed increase in greenhouse gas concentrations. Comparing the statistics of the extreme event in the factual world with anthropogenic forcing to its statistics in the counterfactual world without that forcing. For major heat events in the continental United States, the attribution findings have been consistent and striking. The 2021 Pacific Northwest Heat Dome Attribution Analysis, published within weeks of the event by the World Weather Attribution Team, found that the event was virtually impossible without climate change, that the probability of a heat event of that magnitude in the region was approximately 150 times higher in the current climate than in the pre-industrial climate, and that climate change had made the event's temperatures approximately 2 degrees Celsius hotter than they would have been without the observed greenhouse gas forcing. 150 times more likely, 2 degrees hotter. These are not marginal adjustments to a baseline risk. They are transformations of the risk landscape. For the current event, a formal attribution analysis is not yet available. Attribution analyses require some post-event period for data compilation and analysis. But the physical mechanisms are the same as for the events that have been formally attributed, and the background conditions, global mean temperature approximately 1.2 degrees above pre-industrial, Arctic amplification, continuing to reduce the pole to equator temperature gradient that drives jet stream stability, soil moisture, baselines already lower than historical norms across the Corn Belt due to long-term warming-driven evaporative demand increases are all pushing in the direction that attribution analyses consistently show, making events like this more probable and more intense than they would have been in an unwarmed climate.
The implication for how this event is understood is important and demands honest framing. This is not solely a heat dome story. It is a heat dome story occurring on a warmer planet in a region with lower baseline soil moisture than historical norms, under a jet stream that is exhibiting the wavy, blocking-prone behavior that has been observed increasingly in the era of rapid Arctic warming. The specific blocking pattern is natural atmospheric variability. The intensity of the surface impacts, the speed of the flash drought, the severity of the fire weather, the magnitude of the heat health risk, reflects the natural pattern operating on an altered background state.
At the point where the evidence chain is complete, the honest assessment requires naming 3 genuinely different trajectories for the current heat dome event. Trajectories that differ not merely in degree, but in kind, because the compound nature of the hazard means that small differences in event duration and atmospheric evolution produce qualitatively different outcomes across multiple impact sectors simultaneously. The first interpretation is the outcome that the operational forecast model's central solutions currently suggest, and that would represent the less severe end of the plausible range. In this reading, the blocking ridge begins to erode within the next 7 to 10 days as the shortwave disturbances rotating around it gradually undercut its amplitude and allow the downstream trough to amplify sufficiently to force the ridge eastward. Temperatures moderate from extreme to above normal. Some precipitation arrives in the affected region, not enough to end the drought, but enough to raise fuel moisture contents above the critical fire weather threshold and reduce the ignition and spread risk. In this outcome, the agricultural damage is severe, but does not represent the most extreme losses in the historical record. The flash drought has caused significant crop loss in the most severely affected areas, but the recovery of soil moisture, aided by the returning precipitation, allows some fields to partially recover before the end of the growing season. The fire weather episode produces some large fires in the red flag warning area, but suppression resources are adequate to contain the most threatening starts before they reach community boundaries. Human health impacts are significant, with elevated heat-related illness presentations across the affected region, but cooling centers and public health advisories have reached sufficient numbers of the most vulnerable population to prevent a mass mortality event. This outcome requires the blocking ridge to behave more like the model's median solution than like the most persistent blocking events in the historical record. It requires the dry thunderstorm complex to produce manageable fire starts rather than an overwhelming ignition density that exhausts first attack resources. And it requires the public health and emergency management response to reach the most isolated vulnerable people in the rural affected region, a requirement
that depends on community infrastructure that, as discussed, is not consistently available. The second interpretation is the intermediate outcome that the compound event framework this investigation has built suggests is the more likely range. In this reading, the blocking ridge persists for 2 to 3 weeks total before eroding, a duration consistent with the most persistent documented blocking events in the continental United States and with the current ECMWF ensemble guidance showing low spread around a persistent block solution. In this outcome, the flash drought reaches exceptional drought, D4, status across a core area of the affected corridor. Corn yield losses in the affected area reach the range of 40 to 60% compared to the preseason forecast, producing economic agricultural losses in the range of $10 to $20 billion across the 6-state affected area. The dry thunderstorm complex produces an ignition event of sufficient density to overwhelm initial attack resources in portions of the red flag warning area, resulting in one or more large fires exceeding 10,000 acres that require extended attack response and drawdown of prepositioned regional fire suppression resources. Human health impacts accumulate through the second and third weeks of the event, with heat-related mortality concentrated in the elderly and medically vulnerable populations in rural counties. Emergency department visits for heat-related illness, exhaust, heat illness, treatment capacity at rural critical access hospitals in the most affected counties. Livestock losses from heat stress and forage depletion produce additional agricultural economic damage beyond the crop losses. Air quality impacts from fire smoke affect downwind populations across a multi-state area for periods measured in days. Recovery in this interpretation begins with the ridge's eventual erosion, but extends over months for the agricultural sector. Crop losses cannot be recovered within a single growing season, and the economic damage to farming operations translates into lender stress, equipment purchase deferrals, and rural community economic contraction that persists through the following year. The third interpretation is the one the ensemble's low spread and the historical precedent of multi-week blocking events does not exclude. In this reading, the blocking ridge persists for 3 to 4 weeks or beyond, the tail of the possible duration distribution given the current atmospheric configuration. In this outcome, the flash drought reaches exceptional severity across a wide area during the most critical period of the corn and soybean growing season, producing yield losses approaching the 2012 event's record impacts in affected areas. The dry thunderstorm complex, cycling through multiple rounds as successive shortwave disturbances rotate around the persistent block, produces ignition events over multiple days across a landscape that has been progressively desiccated to the most extreme fuel moisture conditions in the historical record. Fire suppression resources drawn down by the first round fire responses are insufficient for the second round ignition event. Large fires breach containment lines and reach rural community boundaries in portions of the affected corridor. Evacuations occur, structures are lost, the air quality impacts from fires across a multi-state area compound the heat health emergency. Outdoor conditions become doubly dangerous for the respiratory and cardiovascular reasons of both extreme heat and hazardous smoke simultaneously. The compound, human health, agricultural, and fire emergency overwhelms the response capacity of the affected state's emergency management systems, which were not sized or pre-positioned for a multi-hazard event of this duration, geographic scale, and simultaneous intensity across multiple impact sectors. Only the atmosphere's actual evolution, whether the blocking ridge erodes on the shorter time scale of the ensemble central solution or persists toward the tail of the duration distribution, will determine which interpretation this event falls into. Strip it to what the evidence actually says. What is confirmed? A significant blocking ridge is currently in place over the central United States, with 500 hectopascal height anomalies in the upper tier of documented historical events. The ECMWF ensemble is showing persistent maintenance of the block with low spread at medium-range forecast timescales, a configuration associated with lower forecast uncertainty about the block's continuation. Soil moisture values at scan network stations in the affected corridor have reached severe drought-consistent levels in the upper soil layer
on a timescale consistent with flash drought dynamics. NDVI anomalies from MODIS satellite data confirm crop stress across the primary corn and soybean production area of the affected states. 1-hour fuel moisture values at RAWS stations in the red flag warning area are at or below the extreme fire danger threshold across a multi-state area. The atmospheric ingredients for dry thunderstorm development, elevated cloud bases, mid-level moisture from shortwave disturbances, extreme subcloud dryness are present, and the NWS Fire Weather Program has issued red flag warnings accordingly. What is confirmed about the compound architecture, the co-occurrence of heat dome conditions, flash drought, and fire weather hazard is not coincidental. All three are driven by the same blocking ridge. They are physically coupled hazard pathways from a single atmospheric forcing. The response systems managing each individual hazard, public health, agricultural assistance, fire suppression, emergency management, are operating simultaneously on a single event that is producing all three hazard types concurrently. The resource competition and operational coordination challenges of simultaneous multi-hazard response are real and documented from historical compound events. What is uncertain? The duration of the blocking ridge, the single parameter that most determines the total impact across all three hazard pathways. The specific spatial distribution and density of the dry thunderstorm ignition events, which determines whether fire suppression resources are adequate for the ignition load produced. The fraction of the most vulnerable human population that has been reached by heat emergency public communications and has access to effective cooling. What is unknown? Whether the agricultural losses will be concentrated in the currently most affected core area, or will expand with the heat dome footprint over a second or third week of persistence. Whether the fire suppression resource pre-positioning decisions made by the geographic area coordination centers in the days preceding the dry thunderstorm event will prove adequate for the actual ignition load. Whether the cooling center network and public health outreach in the rural portions of the affected region will prevent the accumulation of heat mortality in the most isolated vulnerable populations. The operational meteorologists at the Weather Prediction Center, the Climate Prediction Center, the Storm Prediction Center, and the regional NWS forecast offices are working through a specific operational challenge that the current heat dome event imposes, providing meaningful guidance on a blocking event whose duration, the most consequential uncertain parameter, is the parameter that medium-range models handle least skillfully. The Weather Prediction Center's extended forecast discussions, the technical documents accompanying their Day 3 through Day 7 forecast products, are available on the PC website and provide the most direct window into the meteorological community's real-time assessment of the event. The discussion language, measured, technical, explicit about uncertainty, communicates the confidence level attached to the blocking pattern's continuation and the competing model solutions for its eventual erosion. The Climate Prediction Center's 8 to 14-day outlooks and monthly temperature and precipitation outlooks are the products that translate the medium-range model uncertainty into probabilistic guidance for the timescales relevant to agricultural decision-making and drought monitor assessment. CPC outlooks for above normal temperature probability covering the heat dome region have been running at the maximum or near maximum categorical designation for the affected states. Andy Wood at the National Center for Atmospheric Research leads work on the ensemble streamflow prediction system and related seasonal hydrological forecast tools that integrate the meteorological forecast uncertainty into projected soil moisture and streamflow outcomes, the downstream hydrological consequence of the precipitation deficit that a blocking event produces. His work and the operational implementation at NWS River Forecast Centers provides the agricultural and water resource management community with the most complete picture of how the current atmospheric pattern is likely to affect the hydrological system over the coming weeks. Mark Svoboda at the National Drought Mitigation Center, whose work on flash drought formalization provides the conceptual framework for the rapid drought intensification we have been tracking, is one of the scientists whose ongoing monitoring of soil moisture and vegetation condition data will produce the next U.S. Drought Monitor update. The Drought Monitor, released each Thursday,
and drawing on scan network data, NLDS output, streamflow records, and field observations from state climatologists and cooperative extension contacts, is the most widely referenced document for agricultural disaster declaration and crop insurance trigger assessments. The update covering the current event period will likely show the largest single-week expansion of drought coverage in the affected states since 2012. At the end of this investigation, the evidence has assembled a picture of a compound atmospheric event whose consequences are playing out across three simultaneous hazard pathways: human health, agricultural, and fire weather, each driven by the same blocking ridge, each building toward its maximum impact as the days accumulate, and each connected to the others through the physical and operational threads that this investigation has traced from the 500 hectopascal height anomaly maps down to the 1-hour fuel moisture readings at RAWS stations in the red flag warning area. The primary open loop of this investigation is the simplest meteorological question, and the one hardest to answer with precision. When does the block break? The ensemble says it will. Blocking ridges always eventually erode. The jet stream always eventually reasserts the eastward propagation that carries weather systems across the continent and provides the relief that the land beneath the heat dome cannot provide for itself. The question is not if, it is when. And the answer to that question, given the low ensemble spread currently showing persistence rather than erosion, is not available at the precision that the agricultural, public health, and fire suppression communities need it at. What this investigation has established is the full physical architecture of why this particular atmospheric pattern is as dangerous as the forecasters watching it say it is. Not because a hot summer is unusual, not because drought is unprecedented, not because dry thunderstorms have not started fires before, but because the convergence of extreme heat, flash drought soil, moisture depletion, and dry lightning ignition in a landscape prepared by weeks of evaporative desiccation represents a compound hazard whose total consequence exceeds what any of its components would produce in isolation, and whose simultaneous demands on human response systems are exceeding the capacity that those systems were designed to provide. The gap between what the atmospheric science is showing about the current pattern and what the operational and policy response frameworks were designed to handle is the same gap that appears in every investigation this channel conducts. The hazards compound. The response systems were designed for individual hazards. The preparedness was calibrated on historical event frequencies. The background climate is shifting those frequencies. This community watches because the compound event is where the most consequential stories live, where the atmospheric science, the agricultural reality, the fire behavior physics, and the human health consequence converge in a single pattern that cannot be understood by examining any one element in isolation. We will be watching the blocking ridge for any sign of erosion. We will be tracking the scan soil moisture data as it continues to fall toward and through the wilting point. We will be here when the dry thunderstorm complex develops and when the red flag warning areas expand or contract. We will bring you the ensemble guidance, the drought monitor updates, the fire weather outlooks, and the honest uncertainty about how long the dome holds, every time. Because the question of what happens beneath a heat dome that will not move is not an abstract meteorological question. It is a question being answered right now, in the soil, in the crops, in the fuel moisture of the grass along every fence line in a 6-state corridor, and in the bodies of the most vulnerable people in the path of the most persistent heat event the Midwest has seen in more than a decade. The dome will break. We will be watching when it does, and we will be watching what it is left behind.